programs.
Hello, teacher. Hello, students. Welcome to today's lesson on periodic motion. In today's lesson, we will focus our attention on the energy transformation that occurs when an object performs simple harmonic motion. Are you ready, students? Let us begin. We will start today's lesson with a review activity. In your last unit, students, you studied thermodynamics. You learned about the law of conservation of energy. Can you recall the definition of this law? Please take a few minutes to write it down.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Welcome back, students. I am sure that you had no difficulty in recalling this definition. The law of conservation of energy states that energy may neither be created nor destroyed. Therefore, the total amount of energy in an isolated system remains constant over time. how can we apply this law to simple harmonic motion? We will use a pendulum as our example. An oscillator, such as a pendulum, has a combination of potential and kinetic energy. When the pendulum is passing through the equilibrium position in a downswing, it has no potential energy. However, it is moving at maximum velocity, and it has kinetic energy. When the pendulum is at its maximum displacement, also known as its limit of oscillation, the velocity is temporarily zero. So the kinetic energy must be zero. At this point, the oscillator's energy is all stored as potential energy. As you have already learned, the kinetic energy of an object is the energy that it possesses due to its motion. Kinetic energy is given by the equation energy equals 1/2 the product of mass multiplied by velocity squared. Because an oscillator contains both kinetic and potential energy, we must find an equation for potential energy. To find this equation, we need to determine how much work has been done against the restoring force to move the oscillator to a specific displacement, x. Students, can you recall what a restoring force refers to in a simple harmonic motion? Please write down a definition and then explain why the restoring force is not a constant value.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Hello, everyone. As I am sure you can recall, a restoring force is the force on a displaced object that acts towards its original position. In SHM, a restoring force always tries to restore the oscillating system to its equilibrium position. The restoring force is not one constant value because it increases as the displacement x increases. In order to calculate the work done against a restoring force, we need to consider the change in x. If a mass is displaced by a small distance, delta x, the work done is given by delta W equals force times delta x. Here, we can apply Hooke's law of elasticity, where force F equals the spring constant K times the displacement x. PE equals 1/2 K times x squared. Now that we can determine the potential energy and the kinetic energy of a system in SHM, we can find the total energy by adding these equations together. When an object is passing through equilibrium, its displacement is 0, which means that x equals 0. Thus, its total energy is its kinetic energy. When an object is at its limit of oscillation, its displacement is the amplitude A, which means that its velocity is 0. Thus, its total energy is its potential energy. Students, here we see a graph of displacement and energy. The line at 0 represents the equilibrium position. As the displacement increases, the kinetic energy drops, but the potential energy increases. The reverse happens at the equilibrium position. At equilibrium, the kinetic energy is at its maximum point, and the potential energy is 0. At any point between equilibrium and amplitude, there is a combination of kinetic and potential energy. We have time for one more activity. Students, please use these equations for kinetic, potential, and total total energy to solve the problem.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Hello, students. How did you do? In order to determine the kinetic energy, we can subtract the potential energy from the total energy. In this case, the block is passing through equilibrium. Therefore, the value of x is 0. This means that the kinetic energy is equal to the total energy. Now, we can simply substitute our known values into the equation. Kinetic energy equals 1/2 the products of 25 N over M times 0.24 meter squared. The answer is 0.72 joules. To determine the velocity, we use the equation for kinetic energy and rearrange it to solve for V. We find that V equals the square root of 2 times 0.72 joule divided by 1.8 kg. The velocity as the block passes through equilibrium is 0.89 meters per second. Were these your answers, students? Well done. Today, we have learned that the total energy of an object in simple harmonic motion is both kinetic and potential. We have identified the points where these energies are at their maximums and minimums. And we have derived equations to find their values. That is all the time we have for this lesson. Until next time, thank you, teacher. Thank you, students.